Hi, seventh grade. I hope you are having a fantastic day and that you got a lot done yesterday on your day off from new assignments and got anything missing back in and reported to me so I can get those grades up. So today we are moving into lesson 3. We are combining some parts of 2 into this one so we can get through it a little faster. And our main concept is, how do differences in temperature affect air masses? Okay, because this is going to go into weather. I'm gonna shrink me. Hang on. Okay, so today is Thursday, the 23rd of April. Our agenda today should have been your bell work question, and then this video lesson, and then your assignment on Google Classroom, which will be done in your interactive notebook. Assignments need to be turned in so I can count you for attendance. Please turn in what you have. Daily work, your bell work is due, as well as some entries into your Science Interactive notebook. By the end of this lesson, you will have watched a demonstration to investigate what happens when cooler and warmer air or liquid come together, and know what convection and convection currents are and what cause them. Okay, so all right, so first off, we have a few new vocabulary words. I'm going to move me back over here. Okay, so the first vocabulary word we're going to be working with is air mass. An air mass is a volume of air that has basically the same air pressure, humidity, and temperature, not and. An air mass can be cold or warm. So this is a picture of some very large air masses. Air masses are generally quite large. They can cover a city, they can cover a state, they can cover a big chunk of states. Okay, they can be very large, and they tend to follow a pattern, okay, which is part of why we have the weather the way we have. Okay, the next one we're going to talk about, this is our main idea for this lesson, is convection. Convection is a type of heat transfer in liquids and gases. Energy and matter are moved by buoyancy forces from one place to another due to differences in density. Okay, so keep that in mind. We're going to watch a video, and that is going to show us an example of what happens with convection that we can see. And then we're going to come back to this, and we're going to talk about all these nice big words and how they all work together. Okay, so first, quick reminder, what warms our air? Because we're talking about what happens when air gets heated and moves. So we have our model that we had. The sun transfers light energy, hits the Earth's surface, and absorbs into that through conduction, and then releases that into the air. And the air molecules absorb that heat energy. Okay, so that is a nice little review. So this is our gas convection experiment, and I have to tell you a little story. I have this cool little box, and I tried to make it work for over an hour and a half to 2 hours, and I just don't have the filming specifications or what have you, the right lights. I couldn't make it so you could see it. So I finally gave up and found a video that showed it much better than I did. But just to let you know, I did not set off the fire alarm in my house. So that was always good because it did make a lot of smoke. Okay, so let's watch this.
Thanks for joining us. For today's experiment, we're going to use the gas convection apparatus and learn about heat transfer in real-world situations. If you didn't already know, convection is a method of heat transfer in liquids and gases. Energy and matter are moved by buoyancy forces from one place to another due to differences in density. To demonstrate convection, we'll need to learn a little more about the apparatus first. The gas convection box is a metal box with a sliding glass front and gas exit holes along the top. The setup for use is pretty simple. Place the 2 glass chimneys into the exit holes. Then open the sliding door and light one of the tea light candles. Place it inside the box under one of the glass chimneys and close the sliding door. In our experiment, we want to be able to visualize the movement of the air, so we will use smoke. Hold a smoldering piece of paper or incense near the glass chimneys. You'll notice that as the candle burns, the air surrounding the candle gains thermal energy and expands, making the air less dense than the air in the rest of the box, which creates a buoyant force. The hotter air then rises above the cooler air and out the glass chimney. Cooler air replaces the air inside the box by entering through the other chimney, and a convection current is established. Now that we know how the apparatus works, how can we apply this and find examples of convection in the real world? As everyone knows, fire is extremely dangerous. Building fires can spread quickly and have tremendous energy. As the fire builds, the air and other gases present can rapidly reach extremely high temperatures. Smoke and any gases will therefore become less dense and rise toward the ceiling. Convection is also responsible for the large and small-scale movement of the atmosphere in oceanic water currents. Have you ever noticed how the direction of the wind changes between day and night when you're at the beach? In the mornings, the air over the sand is cool from the lack of solar heating, but the ocean remains warm. This is because water has an amazing ability to hold on to energy, thus it takes much longer to cool. So this causes the air to flow in a counterclockwise direction, or a land breeze. But as the sun rises, it begins to heat up the sand. That hot sand then heats the air above it, causing it to become less dense and rise. On the other hand, the same amount of sun over the ocean has almost no effect on the temperature of the water, and the air over the water remains cooler. The airflow begins to move in a clockwise direction, creating a sea breeze. To summarize, convection happens all around us. From air conditioning in our homes to the ovens that cook our food, the gas convection apparatus is wonderful at demonstrating the transfer of heat. So that's a wrap on today's experiment. If you have an idea for an experiment you'd like to see, comment below. Also, be sure to subscribe so you don't miss any of our future experiments. And as always, have fun learning.
Okay, so that was a really good video that explains how convection works. Now I wanted to come back and look at our definition and explain it. And I've got a little GIF here, and it is actually really easy to see what's going on. So convection, again, is a type of heat transfer in liquids and gases. So right here, I have a heat source, and it is transferring energy into this is a liquid, and so it's transferring it into this liquid. As it gets warm here, it's going to become buoyant. Okay, and buoyant means that it floats or rises. And it floats from one place to another due to differences in density. So we know what happens when we transfer thermal energy into a material. It makes the molecules move faster and farther apart. So if I have cold water and I heat it up, it's going to, the heated part of the water is going to absorb that thermal energy, and the molecules in that hot part of the water are going to move farther apart, and they're going to be, because it takes up a little bit more space, it's going to be less dense, okay? And so it's going to rise. Now, as it gets up here to the top, it's going to start losing some of that thermal energy, and it's going to get pulled back down, okay? Let's look at our next slide. Wish that wouldn't come up. Okay. Oh, this is the wrong one I want. Okay, this one. All right, so this is another video. It's talking about convection currents in a liquid, but it works the same as in a water. In air. What's really nice about this demonstration is it's using the colors in the water to show us what's going on. The first part's a little hokey, but bear with it. Okay, so I'm going to put this on full screen.
Get ready for one of the most hypnotic things you'll ever see in a science class.
Like I said, it's a little hokey.
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up.
Okay, so remember that model?
Here's the thing I want you to remember.
Look and you can see
when
how
water
it's
moves
moving.
from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
All right, so even though that was taking place in water, the exact same concept happens in air, okay? So let's do this as an air current now. So I have a heat source down here. In everyday life on our planet, the sun's energy comes down and heats up the ground. The ground releases that energy up into the air. The air molecules start moving faster because they have more thermal energy, and they move up. As they move up, the cool air needs to move back into the space that was left. And then it just keeps going around and around and around. Okay, that's what's giving us wind and weather patterns and all sorts of stuff. Okay, all right. Now, he talked about how lava lamps work. So convection isn't just for weather. It's not just for tides. You can use convection for a lot of things. For example, how many of your parents have an air fryer? Okay, I do. In fact, I have two. I have one at school and I have one here because I use it so much. Okay, and an air fryer is a convection oven. It's a little mini oven. And there is a fan inside that blows heated air around in a cycle, in a convection cycle. Okay, and that's how it works. So this is a quick video about how lava lamps work with convection. And remember, the same principles can apply to air as well as liquids.
This is so trippy. I could stare at this lava lamp for hours. Wake up, KAMRI. What exactly is a lava lamp? Is this even lava? And how does the lamp create such mesmerizing floating globs? To shed some light on this lamp, I brought on the help of an expert. There she is now.
Wow, Ruby, loft. far out.
Thanks. Are you my expert?
Yeah, I'm Asher J, a National Geographic explorer and a creative conservationist who knows her lava lamps. They're beautiful examples of how science blends with creativity. Now let's see your lamps. Hypnotic, aren't they?
Yeah. So, first question. Am I actually looking at lava?
Nope. Lava is just a marketing name corporations give it. You're looking at two substances floating in harmony.
How exactly do they float in harmony?
To build a true lava lamp, your substances need to have different densities.
So, one substance will sink to the bottom.
The other, and this is my favorite, immiscibility.
What's immiscibility?
It's a fancy science term meaning unmixable. The two substances in a lava lamp are typically water-based liquid and a waxy compound. They can never dissolve into each other. You can see it at home when you combine oil and vinegar. They never truly blend into each other.
Yet they taste great on a sandwich. All right, I see how two immiscible substances form the blobs in the lamp. But how do they rise up and down?
That comes from the power of your lamp's magic light bulb.
Magic light bulb?
Okay, it's a normal light bulb, but the heat from the bulb brings the magic. The heat causes the blobs of wax to rise. As they get further away from the bulb, they cool. Then they fall back down to the bulb, and the cycle begins all over again.
Why does the heat cause them to rise?
For that, we'd have to view the blobs on a molecular level. And there's no way we could possibly...
We could use my molecular shrink ray.
Yeah, we could do that. Honey, let's shrink us kids.
These must be the molecules of the lava lamp's blobs.
As the blob heats up, the molecules spread apart, lowering its density.
And a less dense blob will float towards the top.
Exactly. Now watch. See how the blob cools off? The molecules pack closer together? It's making the blob more dense.
It's amazing to look at a lava lamp from inside its own molecules.
Yes. Can we go home now? KAMRI. KAMRI. KAMRI!
Now that you know how that works, catch up on all the other episodes of How Things Work by clicking right here. And also make sure you subscribe to NAT GEO Kids by clicking down here. See you next time. Bye.
Okay, so that works by convection, and it was really nice to see how they talked about how the molecules spread out, and that makes that blob less dense. The same thing happens with our air currents. Okay, so as it heats up, it adds thermal energy. The molecules move faster and farther apart, and it becomes less dense. So, quick lesson wrap up: hot air will rise, and cool air will fall or sink. This happens when air absorbs thermal energy and the molecules in the air move farther apart and become less dense. The cold air molecules have less thermal energy and are more dense. This makes the warm air rise and the cold air fall. Items, large or small, can be moved in the convection currents. That can include, for example, humidity, water particles, or even if I'm cooking something, have you ever put macaroni into a pot and you see it going like this, okay, inside the pot? That's because it's being carried by the convection currents. Convection can happen on a small scale, in a room, in a cooking pot, in a glass, to large scale, multi-size, state-size air masses, and even larger, okay? And we have a lot of convection in nature. Okay, so the next part is going to be your assignment. You are going to be making a model of convection. Now, I gave you a sample here. Okay, it doesn't have to be very much at all. I made this on my iPad and took a picture of it and put it in. But I have the title. Did you notice my cool little alert? I'm fun. Okay, and then we're just doing one side. So you need to have a red arrow to show warmer air rising, a blue arrow to show cooler air sinking. So here's my red and here's my blue. You need to have black dots for molecules. Now, make sure that you are putting the appropriate number of molecules. So if you noticed, in the hot side, there are fewer molecules per square inch. But on the cool side, there's a lot of them because they're becoming more dense. Okay, then you need to have a heat source. You can draw a fire, you can do something like I did, very simple, nothing too big. So your assignment, okay, fill out the 2 new vocabulary words in your science interactive notebook. So air mass and convection. And those go in the definition section. And then you need to copy the 2 new slides for 423 into your interactive notebook. And, oh, I must have shut where it went. Okay, so, and there's that one, and there's one that looks like this. Okay, this is just an informational page. You don't have to do anything to it, but it does need to go into your notebook. Okay, you need to make a model similar to mine, include your key and all the material or the information on it. And then when you're done, I want you to delete all my stuff. I just want to see your stuff. Okay, so your slide will look more like this one. Okay, all right. Any questions, let me know in the video chat, and I will see you guys later. Bye-bye.